At first, it looked completely ordinary. Meteorologists monitoring weather maps noticed a developing atmospheric system moving across the ocean. Similar systems form every year. Most weaken before reaching land. Others bring moderate rain, gusty winds, and little more than a temporary inconvenience. Nothing about this particular system initially appeared unusual. No record-breaking temperatures, no massive storm surge, no catastrophic forecasts. Yet within days, weather experts around the world were paying close attention. Something had changed. The system was strengthening faster than expected. Its structure was becoming more organized. Its energy levels were increasing. And most importantly, computer forecast models were beginning to show a troubling possibility. What had started as a routine weather disturbance was transforming into something potentially far more dangerous. The warning signs emerged gradually. At first, only a handful of meteorologists noticed subtle changes within the atmospheric data. Satellite imagery showed increasing cloud organization. Wind patterns were shifting. Air pressure readings were dropping. Individually, none of these observations seemed alarming. Together, however, they suggested that the system was evolving. Modern weather forecasting relies on vast amounts of information collected from satellites, weather balloons, aircraft, ocean buoys, radar systems, and ground-based observation networks. Every hour, enormous quantities of data flow into forecasting centers around the world. Supercomputers analyze this information and generate models designed to predict future atmospheric conditions. Normally, forecast models show reasonable agreement, but sometimes they don't. And when multiple models suddenly begin predicting rapid intensification, meteorologists pay attention. That was exactly what happened. Several forecasting systems started indicating that the weather system could strengthen far more quickly than originally expected. Initially, many experts remained cautious. Weather models are powerful tools, but they are not perfect. Forecasts can change. Storms can weaken unexpectedly. Environmental conditions can shift. Still, as each new update arrived, the projections became increasingly concerning. The system continued intensifying. Meteorologists watching the data noticed another unusual feature. The surrounding atmospheric environment appeared highly favorable for continued development. Ocean temperatures were warmer than average. Upper-level wind conditions were supportive. Moisture levels remained elevated. In weather science, these ingredients can create a dangerous combination. Warm water acts as fuel, moist air provides energy, stable atmospheric conditions allow organization. When these factors align, storms can strengthen rapidly. Historically, rapid intensification events have posed significant forecasting challenges. A storm expected to remain moderate can suddenly become severe within a relatively short period. Communities may have less time to prepare. Emergency managers may face compressed decision timelines, and residents may underestimate the potential threat. Researchers have spent years studying why certain weather systems intensify so quickly. The process is extraordinarily complex. Countless variables interact simultaneously. Ocean heat content, atmospheric stability, wind shear, moisture availability, pressure gradients all influence storm behavior. Even small changes can dramatically alter outcomes. In this case, scientists observed several favorable conditions developing simultaneously. The atmosphere appeared primed for strengthening. As forecasts became more concerning, weather agencies began issuing updated advisories. Public awareness campaigns intensified. Emergency planners reviewed preparedness measures. News organizations increased coverage. Despite these warnings, many people remained unconcerned. After all, weather forecasts often change. Storms frequently weaken. Predicted impacts do not always materialize, but experienced meteorologists understood the situation differently. They recognized a pattern that had appeared with increasing frequency in recent years. Weather systems were becoming more unpredictable, and in some cases, more extreme. One factor receiving growing scientific attention involves ocean temperatures. The world's oceans absorb enormous amounts of heat. This heat influences atmospheric behavior in countless ways. When ocean temperatures rise above normal levels, storms can access additional energy. Scientists continue studying the relationship between ocean warming and storm intensity. While individual storms cannot be attributed to a single factor, many researchers agree that warmer oceans can contribute to stronger weather systems under certain conditions. This understanding has become increasingly important because ocean temperature records have shown notable changes in many regions. As the weather system continued strengthening, forecast discussions became more urgent. Meteorologists emphasized not only the storm's current intensity, but its potential future behavior. That distinction was critical. A storm's present condition does not always reflect its eventual impact. The atmosphere is dynamic, conditions can change rapidly, and sometimes the most dangerous phase occurs after initial forecasts are issued. Emergency management agencies face difficult decisions. When should evacuation planning begin? How much risk should be communicated to the public? What areas might be affected? Weather forecasting is never solely about science. It also involves communication. Officials must convey uncertainty while encouraging preparedness. Too little warning can leave communities vulnerable. Too much warning can lead to complacency if impacts fail to materialize. Balancing these challenges requires experience and judgment. Meanwhile, the storm continued evolving. Satellite images revealed increasingly organized cloud structures. Bands of intense weather wrapped around the center. Pressure readings continued falling. Wind speeds increased. Each update painted a clearer picture. The system was strengthening, and it was doing so faster than many had initially expected. Residents in potentially affected regions began monitoring developments more closely. Stores experienced increased demand for emergency supplies. Generators, batteries, bottled water, and non-perishable food items became more difficult to find. Families reviewed evacuation plans. Businesses implemented contingency procedures. Schools prepared emergency response strategies. These preparations reflected lessons learned from previous disasters. Communities that have experienced severe weather understand the importance of readiness. A few hours of preparation can make a significant difference when conditions deteriorate. Scientists studying disaster resilience frequently emphasize this point. Preparedness reduces vulnerability, it improves response capability, and it increases the likelihood of successful recovery. Yet, despite growing awareness, one major question remained unanswered. How dangerous would the system ultimately become? Forecast models continued evolving. Some scenarios showed moderate impacts, others projected far more serious outcomes. Meteorologists carefully examined each update, searching for signs that might clarify the storm's future path and intensity. Then, another concern emerged. The system appeared likely to encounter an area containing exceptionally warm ocean waters. This development attracted immediate attention. Warm water serves as a primary energy source for many powerful weather systems. When storms move over such waters, they can intensify rapidly. Researchers sometimes describe this process as a feedback cycle. The storm draws energy from the ocean. That energy strengthens circulation. Stronger circulation allows the storm to access additional energy. The cycle can continue until environmental conditions change. Historical examples demonstrate how dangerous this process can become. Some of the most destructive storms in recorded history underwent rapid strengthening shortly before reaching populated regions. In certain cases, communities had little time to adjust. Forecasts changed quickly, impacts intensified, and emergency responses became more challenging. As memories of past disasters resurfaced, public concern grew. Weather agencies expanded communication efforts. Emergency alerts increased. Government officials urged residents to remain informed. Social media platforms became flooded with discussions, forecasts, and speculation. Not all of the information was accurate. This created another challenge. During developing weather emergencies, misinformation can spread rapidly. False forecasts, exaggerated claims, outdated graphics, unverified reports, all can create confusion. Experts repeatedly encourage people to rely on official sources and trusted meteorological organizations. Accurate information, they emphasized, is one of the most valuable resources during any weather event. Meanwhile, scientific teams continued monitoring every aspect of the storm. Aircraft flew directly into the system to collect measurements. Satellites provided continuous imagery. Ocean sensors tracked environmental conditions. Supercomputers processed new data around the clock. The goal was simple: understand the threat as clearly as possible and provide the public with the best available information. As the hours passed, evidence continued mounting. The weather system was no longer behaving like a routine disturbance. It had entered a new phase, a potentially dangerous phase, and while forecasters still could not predict every detail, one conclusion was becoming increasingly difficult to ignore. This storm possessed characteristics associated with some of the most significant weather events of recent years. The atmosphere appeared unusually supportive. Ocean conditions remained favorable, and intensification was continuing. The question was no longer whether the system was strengthening. The question was how much stronger it might become before reaching land. Because if current trends continued, millions of people could soon find themselves facing a weather threat far more serious than anyone had initially expected. We followed the development of a weather system that initially appeared ordinary, but soon began showing signs of rapid intensification. Meteorologists observed falling pressure, increasing organization, warm ocean temperatures, and atmospheric conditions that seemed unusually favorable for strengthening. Now the situation was entering a critical stage. Forecast centers around the world were operating around the clock. Every new satellite image was analyzed, every weather balloon launch was carefully examined, every aircraft mission into the storm provided valuable information. And with each passing hour, the evidence pointed toward the same conclusion. The weather system was becoming far more dangerous than originally expected. What worried experts most was not simply the storm's strength, it was the speed at which conditions were changing. Normally, communities have several days to prepare for severe weather. Emergency managers can coordinate responses, residents can secure property, businesses can activate contingency plans. But rapid intensification compresses those timelines dramatically. A storm forecast to be moderate one day can become a major threat the next. And that is exactly what appeared to be happening. Meteorologists noticed that the storm's central pressure was dropping faster than forecast models had initially predicted. In weather science, pressure matters. Lower pressure often indicates a stronger and more organized system. As pressure falls, winds tend to increase, rainfall rates often intensify, and the overall structure becomes more dangerous. The numbers appearing on meteorological screens were attracting attention throughout the scientific community. Several researchers who specialized in storm behavior described the changes as remarkable, not unprecedented, but certainly concerning. One reason involved the ocean itself. Beneath the storm lay a vast reservoir of unusually warm water. Surface temperatures were already elevated, but perhaps more importantly, warm water extended deep below the surface. This meant that even as the storm churned the ocean, cooler water was not immediately brought upward. The storm could continue drawing energy from the ocean for an extended period. Meteorologists often compare this process to fueling an engine. As long as fuel remains available, the engine can continue operating. In this case, the atmosphere was providing favorable conditions while the ocean supplied enormous amounts of energy. The combination created an environment capable of supporting significant strengthening. Forecast discussions became increasingly urgent. Government agencies began issuing stronger warnings. Emergency management teams expanded readiness measures. Evacuation planning accelerated. Public messaging shifted from awareness to preparation. Officials emphasized a critical point. People should not focus solely on the storm's current intensity. They should focus on where it might be heading. Historically, some of the most damaging weather disasters occurred because residents underestimated future changes. A storm may appear manageable early in its development, but atmospheric conditions can evolve rapidly. Experts repeatedly urged communities not to wait until the last moment. Meanwhile, forecast models continued updating. Interestingly, while some uncertainty remained regarding the exact track, there was growing agreement about one thing: the system was likely to remain extremely powerful. Even small shifts in direction could dramatically alter which communities faced the greatest impacts. This uncertainty created challenges for decision makers. Emergency managers needed to prepare multiple scenarios simultaneously. Hospitals reviewed emergency procedures. Utility companies positioned repair crews. Transportation authorities monitored vulnerable infrastructure. Shelters prepared for potential activation. The scale of planning reflected the seriousness of the threat. Then came another concerning development. Radar and satellite imagery indicated that the storm's internal structure was becoming increasingly symmetrical. To the average observer, this might seem insignificant. To meteorologists, however, it represented an important signal. Well-organized storms tend to operate more efficiently. Their circulation becomes stronger. Energy transfer improves, and intensification can continue more rapidly. Some weather experts compared the system to historical storms that had undergone explosive strengthening shortly before landfall. No two storms are identical. Every weather event is unique. Yet similarities in atmospheric behavior often attract attention. Researchers studying previous disasters recognized patterns they had seen before: warm oceans, low wind shear, high atmospheric moisture, strong internal organization. Each factor alone might not guarantee extreme outcomes. Together, they created a troubling picture. As public awareness grew, social media became flooded with images and forecasts. Some posts accurately reflected official information. Others did not. Meteorologists spent considerable effort correcting misinformation. False reports of projected landfalls circulated widely. Exaggerated impact estimates appeared online. Outdated graphics were shared repeatedly. Experts reminded the public that accurate information saves lives. During severe weather events, reliable forecasts become critically important. Confusion can lead to poor decisions, and poor decisions during emergencies can have serious consequences. The approaching storm also highlighted another challenge facing modern societies: infrastructure vulnerability. Many communities were built using historical weather assumptions: road systems, drainage networks, electrical grids, communication systems. All were designed based on previous environmental conditions. But weather extremes have been testing those assumptions more frequently. Engineers increasingly recognize that infrastructure must account for a wider range of possible conditions. A storm that produces extreme rainfall can overwhelm drainage systems. Powerful winds can damage electrical networks. Flooding can disrupt transportation. Communication systems can become overloaded. The consequences often extend far beyond the immediate impact zone. Businesses experience interruptions. Supply chains are affected. Emergency services face increased demand. Recovery efforts require substantial resources. Scientists studying disaster resilience frequently emphasize that the true impact of severe weather depends not only on the storm itself, but also on the vulnerability of the affected region. A powerful storm striking a well-prepared community may produce different outcomes than a weaker storm affecting an unprepared area. Preparation matters. Infrastructure matters, communication matters, and leadership matters. As the storm advanced, researchers continued gathering data. Specialized aircraft flew directly through dangerous conditions. Their instruments measured pressure, temperature, humidity, and wind speed. These observations were transmitted to forecasting centers in real time. Each new measurement improved understanding of the storm's structure. Each mission helped refine forecast models. This process illustrates one of the most remarkable aspects of modern meteorology. Weather forecasting is no longer based solely on observation from afar. Scientists actively investigate storms from within. They collect information directly from the atmosphere. They analyze vast data sets using advanced computers. And they continuously improve forecasting techniques. Despite these capabilities, uncertainty remains an unavoidable part of weather prediction. The atmosphere is extraordinarily complex. Small changes can produce large effects. Storm tracks can shift. Intensity forecasts can change. Impacts can vary significantly from one location to another. This uncertainty does not indicate weakness in forecasting. Rather, it reflects the immense complexity of the natural world. Still, one fact was becoming increasingly difficult to ignore. The storm had exceeded many early expectations. Its strengthening rate surprised forecasters. Its organization continued improving, and environmental conditions remained favorable. Communities within potential impact zones now face difficult decisions. Should residents evacuate? Should businesses suspend operations? Should schools close? These choices involve balancing risk, uncertainty, and practicality. Officials relied heavily on scientific guidance. Meteorologists worked tirelessly to provide the most accurate assessments possible. Public safety depended on informed decision-making. As preparations intensified, weather experts also discussed a broader concern. Events like this appeared to be receiving increasing scientific attention because rapid intensification had become a major forecasting challenge in recent years. Researchers continue studying why certain systems strengthen so quickly. Ocean temperatures, atmospheric moisture, environmental stability, large-scale climate patterns, all are areas of active investigation. Understanding these factors may help improve future forecasts and provide communities with additional preparation time. The approaching storm served as a powerful reminder of nature's complexity. A system that began as an ordinary disturbance had transformed into a major threat. Its evolution demonstrated how quickly atmospheric conditions can change, and it highlighted the importance of science, preparedness, and effective communication. Yet despite all the data, all the models, and all the forecasts, one crucial question remained unanswered. What would happen when the storm finally encountered populated regions? Would it weaken before arrival? Would it maintain its intensity? Or could it become even stronger? Meteorologists continued watching closely. Emergency agencies remained on high alert. Millions of people monitored updates anxiously, because according to the latest forecasts, the most critical phase of the storm's journey was about to begin. And if projections proved accurate, the impacts could be felt across a vast area, affecting communities, infrastructure, and lives on a scale few had anticipated when the weather system first appeared on satellite images. The atmosphere had issued its warning. Now everyone waited to see what would happen next. We followed the birth of a weather system that appeared harmless at first but quickly began showing signs of rapid intensification. In part 2, we examined how scientists, emergency planners, and meteorologists became increasingly concerned as the storm evolved into a potentially major threat. Now the moment everyone had been waiting for had arrived. The storm was approaching land. Forecast centers continued issuing updates around the clock. Emergency operations centers remained fully activated. Millions of residents monitored every new forecast. And scientists watched carefully to see whether the atmosphere would follow expectations or produce yet another surprise. What happened next would become a powerful example of why experts increasingly describe certain weather systems as more dangerous than ever before. As the storm moved closer to populated regions, its outer rain bands began reaching coastal areas. The first effects seemed relatively minor: light rain, occasional gusts of wind, darkening skies. To many residents, the conditions appeared manageable. Some even questioned whether the warnings had been exaggerated. But meteorologists knew better. The outer edges of a storm rarely tell the full story. The most dangerous conditions were still offshore. And according to the latest observations, the system remained remarkably organized. Satellite imagery showed a well-defined circulation. Aircraft measurements confirmed strong internal structure. Ocean temperatures remained favorable. Most importantly, the storm showed very few signs of weakening. In some areas, local officials faced criticism for urging aggressive preparation measures. This is a challenge emergency managers frequently encounter. When warnings are issued early, the threat may not yet be visible. People see calm conditions and assume danger is being overstated. Yet waiting until impacts become obvious is often too late. Experts emphasize that preparedness decisions must occur before disaster arrives, not during it. As the hours passed, conditions gradually deteriorated. Rainfall intensified, winds strengthened, ocean waves grew larger, coastal flooding began affecting vulnerable locations. Road closures increased, emergency shelters reported rising occupancy. Utility companies deployed additional crews. The storm's influence was expanding. Then came another critical development. Weather radar detected extremely intense rainfall bands forming within the system. These bands contained enormous amounts of moisture. As they rotated inland, rainfall rates increased dramatically. Some locations received more precipitation in a few hours than they typically experienced in weeks. Drainage systems struggled to cope. Small streams rapidly overflowed. Urban flooding developed. Emergency responders began receiving growing numbers of calls. Meteorologists were not surprised. For years, researchers have warned that some modern weather systems appear capable of producing extraordinary rainfall totals. Warmer atmospheric conditions can support greater moisture content. When a powerful storm accesses that moisture, rainfall rates can become exceptionally high. Again, this does not mean every storm behaves this way, but when the right conditions align, the consequences can be severe. The situation became increasingly dangerous overnight. Darkness complicated response efforts. Flooded roads became harder to identify. Visibility decreased. Travel conditions worsened. Officials repeatedly urged residents to avoid unnecessary movement. Many weather-related fatalities occur because people underestimate floodwaters. A road may appear passable. Water depth may seem manageable, yet even relatively shallow moving water can sweep vehicles away. Emergency agencies continuously reminded the public of this danger. Meanwhile, the storm continued advancing inland. Wind damage began increasing. Trees fell, power lines were damaged. Electrical outages spread across multiple communities. For utility crews, restoring service became difficult due to ongoing hazardous conditions. Strong winds and flooding created dangerous working environments. As a result, some areas faced extended outages. Power loss introduces a cascade of additional challenges. Communication systems may be disrupted. Water treatment facilities may experience complications. Businesses may suspend operations. Hospitals often rely on backup power systems. And vulnerable populations can face heightened risks, particularly during extreme temperatures. Researchers studying disaster resilience frequently emphasize how interconnected modern infrastructure has become. A single weather event can affect multiple systems simultaneously. Transportation, energy, communications, healthcare, water management all depend on one another. When several systems experience disruption at the same time, recovery becomes significantly more complex. As dawn arrived, aerial surveys began revealing the true scale of the situation. Floodwaters covered large areas. Road networks were damaged. Agricultural regions experienced significant impacts. Rivers continued rising. In some locations, emergency crews conducted water rescues throughout the day. The images quickly spread across news broadcasts and social media platforms. For many viewers, the scenes appeared astonishing. Only days earlier, the system had seemed relatively unremarkable. Now entire communities were confronting major disruptions. Scientists analyzing the event identified several factors that contributed to its severity. Rapid intensification played a major role. The storm strengthened faster than many people expected. Heavy rainfall persisted over some locations for extended periods. Environmental conditions supported efficient moisture transport. And vulnerable infrastructure amplified certain impacts. These observations aligned closely with broader scientific concerns regarding extreme weather behavior. Researchers continue studying whether changing atmospheric conditions may be influencing storm intensity, rainfall potential, and weather persistence. While individual events are complex and influenced by many variables, scientists increasingly focus on identifying long-term trends. One trend receiving significant attention involves rainfall extremes. Several recent studies suggest that certain regions are experiencing an increase in the frequency of intense precipitation events. The reasons remain an active area of research. However, the implications are important. Communities designed around historical rainfall assumptions may face increasing challenges if future events exceed those expectations. Another major lesson involved communication. Forecasting technology performed remarkably well. Meteorologists identified the threat. Warnings were issued. Preparations were encouraged. Yet not everyone responded. This gap between information and action remains one of the most difficult challenges in emergency management. Experts often describe risk perception as a critical factor. People evaluate warnings based on personal experience, past storms, local conditions, previous forecasts, individual judgment. Unfortunately, dangerous weather does not always conform to expectations. Events can evolve rapidly, impacts can vary dramatically, and assumptions can prove costly. Following the storm, researchers conducted extensive analyses. They examined atmospheric conditions, ocean temperatures, forecast model performance, infrastructure impacts, emergency response effectiveness. Their goal was not simply understanding this particular event, it was preparing for future ones. Because, according to many experts, storms like this may not remain isolated occurrences. The atmosphere is dynamic, weather systems continue evolving, and communities around the world are confronting new environmental challenges. One encouraging aspect of the response involved technological advancements. Modern forecasting tools provided valuable lead time. Satellite observations tracked the storm continuously. Aircraft reconnaissance delivered critical data. Radar networks monitored rainfall in real time. Emergency alerts reached millions of people. These capabilities represent enormous progress compared to previous decades. In many ways, society has never been better equipped to monitor severe weather. Yet monitoring alone is not enough. Preparedness remains essential. Scientists frequently emphasize that resilience begins long before storms develop. Infrastructure investment matters. Building standards matter. Public education matters. Emergency planning matters. The strongest communities are often those that prepare before threats emerge. Recovery efforts continued for weeks. Damage assessments took time. Repairs required substantial resources. Businesses gradually reopened. Utilities restored service. Transportation networks resumed operation. And residents began rebuilding. But for researchers, the event provided another important data point, another example of a weather system that evolved rapidly, another reminder that atmospheric behavior can change unexpectedly, and another reason why continued scientific investigation remains essential. Today, forecasting centers around the world continue studying storms like this one. They analyze every available observation, refine prediction models, develop new technologies, and improve warning systems. Their objective is simple: provide better information, earlier warnings, and greater opportunities for communities to prepare. Because weather systems are not becoming less complex. If anything, scientists believe understanding atmospheric behavior may become even more important in the future. Population growth continues, urban development expands, infrastructure ages, and environmental conditions evolve. The challenges are significant, but so are the opportunities. Advances in meteorology, computing, artificial intelligence, and environmental science are providing new tools for understanding the atmosphere. Each improvement helps reduce uncertainty. Each innovation strengthens preparedness. And each lesson learned contributes to greater resilience. The weather system that experts warned about did indeed become extremely dangerous, not because it was the strongest storm ever recorded, not because it shattered every historical record, but because it demonstrated how quickly conditions can change when the atmosphere, ocean, and environment align in exactly the wrong way. It reminded millions of people that severe weather remains one of nature's most powerful forces. And it reinforced a lesson that meteorologists have repeated for generations. The most dangerous storm is often not the one people fear. It is the one they underestimate. As scientists continue studying the atmosphere and improving forecasts, one message remains clear: weather will always surprise us. Storms will always challenge us. But understanding those threats and preparing for them remains one of humanity's strongest defenses.